Okay, we have a bunch of people online. Maybe they're doing that. Okay. Okay. All right, let's get started. I posted all the notes that I hope to get through this semester on Piazza. We may sort of skip through some of those quickly because I'd like to get through to the end. Like in previous semesters, sometimes I haven't actually gotten through to the end. So we might, once we finish up a bunch of the sort of basic microarch stuff, some of the research stuff, we might go through very quickly. And I'll just tell you to go read the papers and then we'll move on because I want to get to the back end of the class, which is the sort of machine learning accelerator specific stuff. But today we're sort of in the middle or the very end of at least the core design before we get into the memory system. And, just to remind ourselves where we were at the end of last lecture, we had sort of built up this pipeline, this in-order pipeline that is massively multi-threaded, that's executing warps. And we mentioned that there's going to be 3 schedulers inside this thing, one at fetch, one at issue, and then there's this other one that orchestrates register file reads. We haven't talked about explicitly how this works yet, but this is what we're going to study today, okay? And so I showed you this picture of what we call the straw man architecture, right? Straw man is like an intentionally simplistic design. And so to sort of remind you what was going on here, the big picture is we have a giant register file, huge capacity with a huge bandwidth demand. We cannot have one highly ported, high capacity structure because that's really expensive from an area and power perspective. So we need to bank our register file and have each bank just have a limited number of ports, maybe one read, one write, or one read write, depending on the design, so that it's tractable to build a high bandwidth, high capacity register file. The downside of this is that now we have bank conflicts, just like our shared memory, okay? Because, if 2 registers have the same bank, you need to serialize their access if that bank only has a single port. So a naive way to build a multi-bank register stage would look something like this, where the input is, this is your input pipeline register. Just to remind you where we were, right? This is your input pipeline register that's coming from the decode stage. So after you've issued the instruction, it will go into a pipeline register and sit here while it does the register read. That's what RR stands for. And then there's an arbiter in here that takes a look at the registers that you want to read from, the registers you want to write to, and then coordinates what bank those registers are in. So there's some mapping that is in the hardware that maps warp register pairs to bank numbers. And it may not be the same. For example, like warp 1 register 0 could be in a different bank from warp 2 register 0. Okay, there's no sort of hard tying between those things. It can be in any bank. And each of these banks reads out a full 128 or 124 bits. Okay, you can think of them as a vector register file that reads out all of the 32 floats that you need for any given usual, register your GPU operation. So it's going to read out all of the information that you need, and then it stores that information on the other side in a pipeline register that basically holds the operands. Okay. You did this in 437, right? You had to read from the register file, you read the contents out of the register file, and then you put them into a pipeline register before it goes to the execute stage. Okay. That's what we're illustrating here. And we have multiple registers on the output because every instruction may have multiple registers that it reads from. And the number of registers you had in the stage is dependent on, the maximum number of inputs for a particular instruction. So in this strawman example, we've got 3, okay? And what this 0, 1, 0, 2, 1, these sort of magic numbers here, this is just meant to represent the data inside the register. So this is a full, 32 values for all the 32 lanes that we're going to operate on inside the SIMD unit. Okay, questions on this so far? Does this make sense to everybody? Why do I have what is this thing here? What is this? It's written on the slide. It's a crossbar. What is a crossbar? It's an interconnect. That is basically an all-to-all interconnect, right? So basically, we need to be able to connect this bank to any one of these output, pipeline registers to hold the output, depending on what operand you read. So this crossbar orchestrates that. So, basically we'll set up the arbiter is going to set up the crossbar such that you can spray out whatever is read from whichever bank to whichever input operand register it needs to go in, okay? So this seems fine, but the downside of this is that if I have bank conflicts, I'm serializing because, like, let's say, for example, that these two input operands both live in the same bank, which I believe in this, straw man example, they do. That means that on one cycle, I would read one out from bank 0, and then on the next cycle, I would read one out from bank 1, and then I'm generating a bubble in my SIMD unit, which is bad, right? So this is like hyper optimization. So when we talked about the optimizations that occurred in a GPU pipeline, like the very first thing you want to do is make sure that global memory accesses are good. Then you make sure that shared memory accesses are good. And now we're down into like the cycle by cycle issue to the function units and making sure that the register file is actually being used to its maximum capacity. And if you really want to run like the densest of math and have it operate at peak compute efficiency, this has to be right. And so if I had a whole bunch of math operations and they had bank conflicts in them in the register file, I'm going to kill my compute efficiency because I don't have enough bandwidth out of the register file. Okay. So this straw man works, but it's slow. Questions? How can I fix it? What are options to fix this? Yes. Have multiple instructions in flight. I think I told you this last class, right? There's multiple instructions in flight, and that's essentially what we're going to do, right? So right now, I've only got one instruction in flight in the register read stage, right? I go from issue, I go to register read, and then in this straw man example, there's just a single instruction. But at any given time, maybe I will want to have more than one instruction in flight. And then if I have, let's say, 8 instructions in flight in my register read, then hopefully there's enough conflict-free reads that I need to do that I can keep the register file busy 100%. Okay, and that is generally the concept behind what we call an operand collector. So this is just, so this is real. Okay, how do we know? Some of the white papers actually contain the term operand collector. They still do to this day. They've never really explicitly said what this does, but there's a patent that this particular lecture is based on. Like these pictures that I'm showing you are pulled from a patent that NVIDIA created to talk about building a highly multi-threaded register for GPUs. Okay, so that's where this sort of comes from. And the bank conflict thing, hopefully this is intuitive to you, right? So if R1 and R2 are coming from different banks, then there's no conflict, there's no problem. If R0 and R4, for example, are coming from the same bank, then there is a conflict and you're going to have to serialize. Now, the compiler can help you here, as I mentioned last class. If the compiler knows the mapping, the compiler can try to create instructions that do not, it basically can add that secret sauce to its register allocation mechanism, and then it will try to make sure when it puts a new instruction like when it generates a new machine instruction, that they will have no self-conflicts. Right? If it adds this constraint to the register allocation mechanism, it can say, all right, I want to do a mul, and I want R0 and R4 to be the 2 inputs, but I know this is going to create a register conflict, so I'm going to move the contents of R4 to R5, and then do the multiply on R0 and R5, which I know had no conflict. But this makes the compiler's job harder because now there's like this extra constraint and it's going to have some extra moves to move things around to account for the conflict. So it's a pain in the butt to rely on the compiler to do this. And sometimes it's kind of unavoidable or not, or very difficult to avoid without an excessive amount of moves because just of the way the program is generated. Who does stuff in compilers here? Is anyone doing stuff in compilers, right? So if you're adding this new constraint where certain registers cannot be used together, it limits the amount of optimizations the compiler can then do and adds overhead, et cetera. It's doable, but it's not ideal. So we want something in hardware that can ideally sort of make this work without forcing the compiler to fix the problem in the static code. And then the compiler also has to be aware of the mapping, right? Which means that every generation, you're going to have to change your allocation algorithm to adapt to the new mapping if we decide to increase or decrease the number of banks or whatever. So it makes it more difficult to sort of revise the hardware. Okay, so here's an example. This is sort of a working example of what happens with, I think, our very simple straw man. Okay, so let's walk through how this goes. So we've got two instructions in the program, mad and an add. So mad stands for fuse, multiply, add. So it multiplies two things together and adds another one. So there's 3 input operands, and the add has 2 input operands, and they both have 1 output operand. What we're showing on this here is the decoded cycle. So we're going to start from cycle 0. And so on cycle 0, we're going to assume that, warp 3, and again, why warp 3? Well, that's just what the issue scheduler picked, right? This could be anything. But let's say that warp 3 ends up decoding. So you issue, and then sort of, we're saying decode, but really this is issue. We issue this instruction from warp 3 that has this multiply add instruction, and it needs 3 input registers. And in this toy example here, I'm showing you with the subtext what bank each of those registers live in, okay? And this is just based on a mapping. This mapping can change, but in this example, I'm assuming that R5 lives in bank 1, R4 lives in 0, and R6 lives in 2. And so for this first instruction, is there a problem? Yes or no? For the instruction decoded on cycle 0, is there any problem? Not right now, no. All 3 of the inputs are in different banks. So that means that, if I take a look at the read, so what I'm showing down here is cycles and the reads that are performing and the writes that are being performed on each bank in any given cycle. So if on cycle 0, I did the issue of this mad instruction, then on cycle 1, it'll be in the pipeline register, right? And then I will do all of the reads for warp 0. So warp 0, instruction 1, R4, R5, R6 are all read, and I'm getting like 75% bank utilization out of my register file, okay? Makes sense? Then in the next cycle, after I've read it, the execution unit can actually use it, right? So I read the values out, I put them in the pipeline register, then the next cycle, the execution unit can read all of those values out. And what I'm showing down here on this row is the activity of the execution unit. So the execution unit is going to be doing the operation for warp 3 because I just read all of its operands on the previous cycle. Okay. During cycle 1, so we decoded the first instruction on cycle 0. Then on cycle 1, let's say that warp 0 gets selected, and let's say warp 0 is a little further along, and it's I2 is what we want to execute. If we look at I2, does I2 have a problem?
Yes.
Yes, right. I2 has a problem. I2, R5 and R1 both map to the same bank, which means that there's a serialization here. I cannot, in one cycle, read all the operands I need for I2. So I have to serialize them. So in cycle 1, so in cycle 0, I sort of decoded that first instruction. In cycle 1, I decoded, this other I2 instruction. And remember, this is from a different warp. Okay, these are all different warps, so there's no cross dependency between any of these instructions. And I have to serialize it. So I just pick one of them. Let's just use a simple lowest first ordering. So I read from R1. So in cycle 2, I read the R1 value that's going to satisfy that I2 instruction. And then I'll have to read the second operand in cycle 3. Right, which means it takes me 2 cycles to read my operands now. So there's actually a variable latency register read here. And also happening in cycle 3 is the write back, because we're also going to have to write to the register file. So the write back from W3's execution, assuming that we had a 1 cycle execution unit latency, which is somewhat reasonable in some cases, it's going to write back, and it's going to write back, thankfully, to bank 2, so it's not conflicted with that read from the other I2 instruction, okay? Questions so far? So we're sort of, at this point, we're kind of here. Makes sense? All right, in the next cycle then, I have the input operands R5 and R1. I've already read them in the previous two, so that means the execution unit is going to get to use, W0 is going to get to use the execution unit, and W0 is then going to write back in the fifth cycle to R5. Okay. Now, what else is happening here? So in this particular example on cycle 2, I only have one pipeline register, right? So that pipeline register is holding this I2 instruction. So on cycle 2, I couldn't actually decode anything. On cycle 3, at least in this example, I'm not decoding anything because I'm assuming that that's held. And then on cycle 4, I can go ahead and decode, or for whatever reason, let's say, maybe the front end is stalled, right? And then on cycle 4, I can go ahead and decode this next instruction. Again, this instruction has the same bank conflict because in this mapping, we're assuming that all the warps actually have the same bank mapping, which is bad news, right? You don't really want to do that. You usually want to move them around because if you have some pathological mapping, it'll continuously happen. But if you want the compiler to have a consistent way to map things, then you want them all to have the same mapping, right? So there's sort of this tension between providing something that's consistent for the compiler or providing something that's sort of sufficiently random that, most of the time you don't end up with bad accesses. But in this particular example, we're assuming that every warp has the same mapping, which means that this next instruction is also going to produce a conflict. So it gets decoded in cycle 4. And then I want to read from this warp 1 I2, right? So actually, I think this diagram is wrong. Yeah.
That should be I3, right?
This should be 3. I think I fixed this before and I keep deleting the fix for some reason. This should happen in cycle 3 because on cycle 4, you actually do the read, right? That should have been 3 and not 4. I'll fix it in the post slides. Okay. So you decoded it, it gets into the pipeline register, and then you perform the read. And then it gets additionally delayed. Why? I can't actually do the second read right away. For what reason? A bank conflict with what? The write back, right? Because the write backs are also happening at the same time. If I assume I have only one read write port on each of these banks, which is more efficient to implement, then I have to wait, and generally we'll prioritize writes over reads because the writes are going to complete the instruction. So the write would complete from warp 0, and then in the next cycle, I'd finally get to read the next value from warp 1 I2. And then this would carry on, right? And then in the next cycle, it could use the execution unit also. Questions on this? Yeah.
So why are two different warps working on the same instruction?
So the code, remember how GPUs work, right? The code that everyone is executing is the same. Because they start with the same program. The kernel everyone starts with the same program kernel, all the warps of the kernel. And so this is very common that they'll be executing the exact same code, but it's on different registers, right? Because they each have their own different thread private registers, because that's where they're doing their computation. Okay. So yes, they're executing by and large mostly the same program counter values, but they're operating on different data. Yeah.
So the registers between different forms map to different physical registers. So why should the R5 on warp 0 and R5 on warp 1 be the same?
So in this example, we're assuming that they are for simplicity. It's an overly simplistic mapping. This, like I said, this does actually make your compiler's life easier because it's known what the mapping would be. Because if you think about it, the compiler doesn't know which warp is what, right? It's just producing one code that they're all going to use. And if the mapping is actually different in different warps, it can't possibly know how to schedule it. But you end up with these bad pathologies because the same instructions will want the same banks, and the programs tend to be at the same place, right? The warps tend to be kind of going at the same rate, so they're always going to want the same banks, and that's bad news. Okay. Other questions? I always have some kind of question on that looks like this on your exam. Okay, as a forward pointer. on like, do you understand how the register read? I don't know, we'll get to the operand collector, which is the way it actually works, but if you don't understand this, then it's gonna be harder to understand the next part. I think this is pretty simple, but please ask questions if you don't understand it. Yeah.
I guess like just a follow up on the last question. So like, why couldn't you in the hardware just bank instead of banking like register identify like bank across thread, like thread registers?
Oh, so like stride the vector across different registers, more like happens in shared memory, how you sort of like each lane is a different bank. You could do it that way. So if you did it that way, what would that mean? That would mean that your banks would be really narrow because now you've got 32 byte wide banks. And that loses you some efficiency generally, especially if most of the time you are reading from all the lanes at once. And does it help with throughput? Well, I mean, so that means that you still have this problem where, so let's say I just banked it 32 ways at 32 bits wide each, right? So a float each. If I have two operands I need to read, unless each of those are dual ported, I'm still screwed. It doesn't solve my need to read 3 or 4 operands if I bank it that way.
Right. Yeah, I guess I meant like, or maybe bank it like both by register and by,
Both ways. Yeah.
then maybe it will become.
So there is, in reality, there is some sub-banking beyond this, like they do slice things statically where it's not 32, it's, 4 or 8. But then it's more like a Warsaw, it's always going to do it 4 times, right? Kind of thing. So there is additional sort of sub-slicing that happens, but at a logical level, you're always, if you say you're going to read, the next 4 cycles are going to be reading these values from the RF. Makes sense. But yeah, banking that way saves you across the warp, but it doesn't save you anything if you've got more than one, or it saves you for one read across a warp register, but it doesn't help you from multiple warp registers being read. That's a good observation. Other questions? Okay. Okay, so that's that example. So let's fix this. So this is what they actually do. Instead of this straw man, they have something called an operand collector. And so what happened here is that we've replaced that single pipeline register that stored one instruction in flight in the register read stage. And we've replaced it essentially with a whole bunch of what they call collector units. And each collector unit is sort of, it kind of operates a little bit in the way like a sort of conventional processor works. Like, maybe that's a bad analogy, but let me just explain how it works. So after you've sort of decided to issue this thing, you will pick one of these, in this case, 4 collector units to basically allocate for this particular instruction. Okay, so in this example, I have 4 collector units, which means I have 4 instructions from 4 different warps in the read register stage at the same time. Okay, so after I do the issue, instead of just dumping it into a single pipeline register, I check to see if I have any free collector units. Each of these as an individual is a free collector unit. If I do, then I consume that collector unit, and that basically has buffered storage for all of the operands that this instruction needs. So instead of just having like a single value on the output for each pipeline, in the pipeline register, I'm essentially going to have multiple pipeline registers that I'm accumulating over time. So I've got a bunch of extra storage in here to keep the values that I'm reading out of the banks. So that way I can spend several cycles reading them out and then time slice the accesses to the banks over all of the warps that I've got in flight. That is the basic idea. And so what this picture shows is, what is this showing? So basically this is saying that warp 0 had a MAD instruction. It needed 3 input operands. None of them have actually been read out from the register file yet. That's why these things are zeros. And this is the data that it's meant to, so there's actually like values in each. So similar to reservation stations, right? You've actually got the values. It's not a reservation station. We're not doing it out of order, right? But we've got the values there right before the execution units so that they can sort of buffer the inputs for multiple instructions at the same time. And, each of these in this example is coming from a different warp. Why is that important? What do I break? What do I potentially break if I allow two instructions from the same warp to be in this thing at the same time? Yeah, the order of operand reads. Because I could potentially finish the reads of these things out of order. And remember, I said that there were no read after write hazards in the GPU pipeline because I knew that all of the operand reads were going to happen in order. If I allowed two warps or two instructions from the same warp to live in here at the same time and didn't guarantee that the oldest one finished first, then I could have a reordering here, which would violate that dependency. But so for simplicity, in the patent anyway, the baseline that they describe says that only one instruction from each warp can be in here at a time, which is fine if you have enough warps, because who cares? Like you don't need the ILP from each individual warp. You can just go to another warp to get new work. And so here, the configuration is roughly the same. We have still 4 banks, so we haven't changed the configuration of the individual main register file yet. We've got this arbiter that is still scheduling. So this is the third scheduler. Okay, so remember I showed you the thing with like the 3 loop approximations and the 3 different schedulers. There's the issue scheduler, or there's the fetch scheduler, there's the issue scheduler, and then there's this scheduler that is attempting to maximize register file throughput by scheduling from all of these warps that are in flight in the RF stage. The upshot of this is that your register read now is potentially non-deterministic in latency. Right, it may take 1 cycle, it may take 3 cycles, and that's actually dependent on the contention in the register file at any given point. Right, because if you just had 1 warp flying through there versus all 4 of them, it may take you longer when there's 4 than when there's 1. So there's no question on how they actually deal with this. Remember, I told you they put the encodings in the instructions for how many cycles this is going to take. Most likely they just do the worst case analysis and build that in. So it's definitely done by them. So the Operand stage can take a shorter amount of time, but they probably don't actually utilize that because, I don't know, that's not important. That's the guess anyway. Okay, what else is important here? Right, so this arbiter's job is to basically take in the whole gamut of registers and banks that need to be accessed in any given cycle and then create a conflict-free schedule. Okay, which is a pretty simple algorithm. Like this is in hardware, right? This is happening at the nanosecond level to try to orchestrate the register reads every single cycle. But this is not necessarily a difficult circuit to construct. Are there questions on this before I go through the example? What's the trade-off here? What have I added to allow this to happen? Is this ISO area with the previous solution? You're saying no. Why not?
The extra registers to extra buffers to hold all of them.
Yeah. I added all this buffering over here. Before I just had one, because I only have 1 instruction in flight. I only need to satisfy, 1 instruction if I'm only satisfying 1 pipeline. Of course, you scale this up to multiple pipelines. There's multiple, pipeline registers. But for this simple example of just a single pipeline, you just need 1. But now I've got N because I've got a bunch of these in here buffering. Okay. And now my interconnection network becomes slightly more complicated as well, because now I've got multiple targets, right? Depending on how many operand collectors or collector units I scale. The more collector units I put in there, the more potential parallelism I can keep in my register read stage. But the more complex everything gets, and the worse it scales as you go up, because crossbars are expensive. So you don't want 64 collector units, right? In this thing. Now you've tried to make an efficient register file and then just threw all of that away to like put way too many collector units in there. Now your crossbar is insane. So this is a sort of design trade-off. Other questions? Okay. Blah, 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 blah. Right. So how does this work? So here's a timeline example of the register file in flight. And this particular example, we're also going to change the bank mapping. So there's a table, and such a table exists, or at least a mapping function exists in all GPUs that will map the warp register number to the particular bank that warp register number lives in. So if we looked at before I could label the code, right, and say what bank everything lives in, the static code. Now I can't, because now every instruction, what bank it be dependent on what warp it is from. Okay, so I'm going to put the bank labels now as a subfield of the issued instruction, because it matters what warp issued it. So in this example, we start out with on cycle 0, warp 1 goes to instruction 1. Thankfully, we've got a situation where it has 2 that are independent. Okay, we have 2 registers that are independent, but I'm only reading from 1 in the next cycle. Any guesses as to why in this example? So in cycle 0, I issued an instruction where I would read from which 2 banks? Are you following me at least that far? 3 and 2, okay? Because R2 is in bank 3, R5 is in bank 2. But then if I look at my diagram of what happens across the banks on each cycle, I'm only reading from 1. Why do you think that might be?
So then you read from the same bank in the next.
Nope, that instruction is not there yet. Nope. I was making an implicit assumption. Well, in this one, okay, so let's go back to the straw man. In the straw man, I assumed that all 3 destinations for all 3 input registers that I might need for this instruction are logically separate memories, right? So logically individual registers, which would mean that if I read and I needed all 3 input operands in one cycle, I could write all 3 input operands to all 3 of these registers in that same cycle. Sorry, 3, not 4. Okay. When I changed it to do this, what did I do? That's different. Still have 4 things coming. Let's assume that
You can read it from multiple banks at the same time, but you can't write it to the same collector.
Exactly. Unless I dual port my collector units, then I can only my collector unit bandwidth. Because remember, every read requires a write. Right? As you read something out of one structure and you're putting it into another, that there's a read write thing happening on that cycle. And in this particular diagram, if I don't scale up each of these to handle, n potential writes every cycle, then I really can only read one value out. And, that's probably the more efficient way to build it. The downside is that now you are creating serialization for a single warp. But the upside of GPUs is that we just don't care. We just don't care that one instruction is going to take longer to go through this, as long as in the aggregate, if we have enough instructions, the thing is kept busy. Okay. So the reason why on this very first cycle, we had a conflict-free read potential, and we didn't actually do it, is because the collector units that you're writing into are single ported to make them efficient area-wise. Okay. Make sense? Questions? All right. So that's the first cycle. On the next cycle, so I just chose to read from bank 3 for this one. And then on the next cycle, while I was reading from bank 3, I also decoded this next, issued this next instruction. And then on cycle 2, what I can do is do the other read. So I'm reading, what am I missing here? I did R2, so I need to read R5. So that's what this is. And then I can also perform one read on this one. So this is warp 2 R2. I can do this one in the same cycle. So as you fill the pipeline, you'll start to be able to use all of your banks at the same time. But in the beginning, you can really only do one because you only have one instruction in flight. That's what's happening here. You're sort of filling up the pipeline with all of these register reads in flight. So then we can do those 2 reads on the next cycle. In this scheduling algorithm, first prioritizes writes, okay, and then reads second. So finally, after 2 cycles, my execution unit is, and remember, this is what we actually care about at the end of the day. Like once the pipeline is full, what we want is the execution unit doing something useful every cycle. I don't care what warp it comes from, but just give me work that that is basically flowing through the max, that is using the floating point units. And even though you're sort of serializing things so it can't get started right away, it's the same principle as pipelining, right? You're sort of keeping it busy much more frequently because you've got way more things in flight. Okay, so then on cycle 3, we do a read from, warp 3. Again, you can sort of, I don't know, who wants me to go through this in detail? I do go through it in detail in a video. I will ask you a question, something like this on the exam. With those 2 facts in mind, who wants me to sit here right now and go through it? 1, 2, 3, 4. All right. Let me do it. Okay. So cycle 1 we got, right? We're good. Cycle 2, we're also good, right? Because we basically just finished off this instruction. And then on cycle 2, we're also doing one of the reads from, which one? We're doing our 2 read from this instruction, okay, on cycle 2. So we explain what happens here. Good so far? People who want me to do this? Okay. On cycle 2, we also ended up decoding and issuing this next instruction. So this new one is coming in and it's grabbing a new collector unit. Yeah.
Just to be clear, when you're writing to 2 different operand collector units, you can just like
Then that's cool because each of them is their own, it has their own marker. Yeah. Okay. So what I want is many warps in flight and many potential. I want all 4 of these to be lit up every cycle, ideally, once I fill the pipeline. And this is the beginning of the pipeline, which is why it looks crappy, because they're empty at first and you need to fill them. Okay, good question. Other questions so far? Okay. So yeah, you'll notice that if I look across the reads, right, I'm never reading into the same warp in the same cycle because I need to read into a separate collector unit. Excuse me. Okay, so where were we? So we finished off cycle 3 here, right? And in cycle 3, warp 1 finally gets to do its work because it's read its 2 operands. In the next cycle, warp 2 gets to do its work because it's read its 2 operands. If we look at like warp 2 R2 and warp 2 R5 are both good to go. And then we also need to schedule a write back. Okay, and this write back is dependent on how long the EU takes. In this particular example, we're assuming the EU takes 1 cycle. So that's going to claim, if we take a look at where this one wanted to write back to, it wants to write back to bank 2. So it's going to claim, we're going to assume there's just 1 read write port on each bank. So if you're doing a write, you can't do a read in the same cycle. So it's going to write back warp 1, R1 in cycle 4. And then we're also going to perform 2 more reads. So we've got a new thing. So in cycle 4, we've got warp 3 in flight, and we've actually got warp 0 in flight because now we've filled all the collectors at this point. So we can basically perform 1 read from warp 3. We can read R5, and then we can perform 1 read from warp 0. We can read R3. And then in the next cycle, so yeah, something weird happens here. So 3 gets to go. Okay, so that's this one. So at this point, I've done all 3 of these instructions. I might get, or they're at least in the execution stage by the time I get there. And the other ones are writing back. So let's look at this one. So what is happening with this guy? So if I look at W0, I decoded it in 3. I read the first read in 4, and then because of the way I chose to read from bank. Is there a bug here? R3 comes from 3. 331. Where's his R1 read? It's not on here, right? Yeah, it's not on here. So because of the way I chose to schedule the reads from warp 0, so if I look at what it needs to read, it needs to read twice from bank 3 and once from bank 1. And so bank 1 is available here, but so is in cycle 4, bank 1 is available, but so is bank 3. And I just chose to read from bank 3 in that cycle. And then for whatever reason, the arbiter is saying, it's trying to do them essentially in order, right? It's trying to say, I want to read the first operand first and the second operand second and the third operand third. And it's not choosing to read R1 from bank one in this cycle where nothing is happening because the scheduler is constrained in that way. An more intelligent scheduler would try to overlap them. So here we end up with just one write happening because this one is saying, oh, I need to read from bank three, but bank three is busy with the write from the previous cycle. And then finally, that clears, and then it does its read from bank three. Then in the next cycle, it'll read from bank one, just because the scheduling algorithm in this example is stupid, right? And so if you had a better scheduling algorithm, you get more throughput out of this thing, basically. Okay. Questions on this? This table here is simply just showing the mapping. So these are the 4 banks, and then it's not consistent across every warp. So every warp will have a different bank mapping. And this table that is here is, what we call swizzling, right? Like just trying to like move around and offset the registers in every bank so you don't end up with these pathological conflicts. And so the patent shows that, this combination of doing this intelligent collector unit thing and doing the swizzling improves the throughput of over the strawman by 2x on average, which is significant when you're talking about, this is the difference between, a gigaflop and half a gigaflop with, it's big. Questions on this? Yep.
So between banks, you overlap from different warps. Does that include the execution unit as well? Where you can have like one.
So in this example, we're assuming we just have one pipeline. We just have one execution unit, and there it's only ever used by one warp instruction at a time. So there's no situation where I can dual issue to from the execution
You
unit.
can't read from the same warp, right? Like in cycle 3, you can't read from warp 1 because the execution unit is.
You don't need to, right? Warp 1 has already got all of its values.
Okay.
And if we only have one instruction from warp 1 in there, then by definition, there's no demand from warp 1. Makes sense? Now, if you have different execution units, you can do this in different ways. You can have every execution unit have its own collection of collector units, sort of like reservation stations, right? The FPU will have its own reservation stations. The integer pipeline will have its own reservation stations. Or you could unify everything and then have them share a pool of collector units. And again, that's a design trade-off, whether you want to do that or not, as the GPU designer. I think in general, they have separate collector units for separate pipelines to try to simplify things. But that doesn't have to be true. Other questions? The scheduling obviously gets more complicated if you have more EUs to contend. Yeah.
In that first instruction, we the operand collected most the operands in it.
Yeah, good question. So I just went to 4. So as soon as the thing is done, so if we take a look at the configuration here, so like let's say this one, right? I think it's read all of this instruction, for example, has read all of its inputs. If the execution unit is free and we're saying that warp 2 is good to go, then you can basically send it on down to the next pipeline stage. Now, it's a design decision whether you can also fill it on the same cycle. It depends on the circuitry. Like, are you allowing it? Is there enough time in the cycle to actually write it out? And then it's like register file, right? If you want to do the read and write it in the same cycle, that's a design decision. But in theory, as soon as you've done the execution, it's free and you can fill it. Whether that's on this cycle or the next cycle, it's based on your circuitry. Okay, good question. Yeah.
So like waiting for writes, that's the.
So waiting for writes is a separate issue because the operand, yeah, that's a good point. So the operand collector doesn't need to accumulate the writes, right? It's just for the read values. The writes are going to be produced on the other side, right? The writes are produced over here. And then essentially in this example, it's just one bus. It's a write back bus that's going back into the register file, and it's wired up to the arbiter, which will basically, check to see which one it wants to go to and then give it priority. It doesn't have to give it priority, but if you don't, then you're blocking, right? Because now, you're not actually clearing the EU on that cycle. So that's why writes generally have priority to clear the EU, so the next one can be issued technically. So we don't have to buffer the writes in the operand collector, we're only buffering the reads. Yeah, which is different from reservation stations, right? Where we're sort of we're playing these games of producing values and then fixing the dependencies and sharing them through the reservation stations. We don't need to do that here because there's no out of order. And the only way that we're communicating values is through the RF banks. Okay, makes sense? Good question. Other questions? Yeah.
What happens if you have like two operand card units fill up by the same cycle? You just like issue like the highest priority.
So if you had two, so if you allocated two operand collector units in the same cycle,
Yeah, both of them get full.
so if the operand collectors are per EU and your issue scheduler is only able to issue one per execution unit, then that's impossible. Okay, because basically it's sort of like a pipeline register. Like after I say issue, I'm going to go to this next, and I can only do one issue. I just decide what one warp to issue that cycle. If I have done it such that, and that's part of the reason why I think that they mostly keep collector units to be pipeline private. So like there'll be one for the special function unit, one for the integer unit, one for the MAC units, whatever, like one set of collector units. If you didn't do it that way, and you were doing dual issue to the different pipelines, then you would consume more than one collector unit in one cycle. That's doable. But now you have to have the logic to correctly select which one. And then now all of a sudden the arbiter just has way more choices on the next cycle of what to schedule from. But you'd have to write into two collector units in one cycle instead of one, or n collector units instead of one, depending on the extent of your issue. Does that answer your question? Yeah. Other questions here? These are all very good questions. Yeah.
Doesn't this break like a method of like ensuring the raw elements don't have to bind critics, they have to compile it certainly suddenly.
Yeah, because now the register read is variable latency. Because sometimes, like I said, if there's no warps in there, you may finish your reads quicker than if there are warps in there. There are two ways that they could solve this. We don't know what they do. Okay. One way is they worst case it, and they say that I guarantee that given this many collector units, and they prioritize the scheduler so that they don't stay in there for any longer than n cycles based on how many operands they need to read, and then they worst case it. So the value is ready, but then sitting there waiting. Worst case. The other extreme is that they do it post operand read. So we allow the operand read to be potentially many cycles. And since I'm not issuing again from that warp until it's cleared the operand read anyway, I know that it's stalled. I let it spend 7 cycles, 4 cycles, 3 cycles, whatever it takes in operand read. And then I encode in the instruction everything after operand read. And that's what gets used to clear the dependencies. And so you get your variable stalling from the sort of runtime throughput contention, and then you get your fixed latency solving, and you still don't need a scoreboard, because essentially this is now like the barrel execution for this stage, right? I only have one instruction from each warp in flight every time. It simplifies that logic. That's a really excellent question. And it's most likely that they actually do it that way, because otherwise the worst casing is kind of a pain in the butt. Like you need to prove that there's no way that this could spend more than this many cycles in the operand read stage. And what if there's a lot of stuff writing back? Like it sounds trickier to do. You'd have to be overly conservative, which maybe hurts performance. Good question. Other questions? That's an excellent question. Whoever thought that reading register operands could be so complicated, right? In order pipeline, no less. Like, come on, this is simple, right? Yeah. And they still do this to this day. There's good evidence that this is still in modern processors. We actually did a paper on like trying to make the issue scheduler more aware of bank conflicts to try to make this better. Make the scheduler's life easier here by using the issue scheduler to try to mitigate bank conflicts that we know are coming further down the pipeline. Anything else? Okay. Blah, 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 blah. That's it. Okay, that's it for read operand. Let's go to the next thing. What was he gonna do next? 15 memory system, okay. All right, so we're still in the core. This is really weird. My cursor is moving my iPad, but it's like, why is this happening to me? Look at this. All right, there we go. Okay, here we go. All right, so we're gonna move on to the memory system. We're gonna start with the sort of lowest level of the memory system, the stuff that's closest to the core. There's 5 different flavors of this just from CUDA, from your knowledge of CUDA. We're gonna have to implement something that handles all of these. So there's locals. This is for stuff like stack memory, things like local arrays. There are special memory accesses that says that this data is thread private. Okay, it means that no other thread can touch it. So there's certain things I can do to make that efficient. And we'll talk about that. You don't usually explicitly program locals, they just kind of happen. When you put a local array inside your CUDA program, it'll end up using locals to store that array. If you're calling functions and it's using the stack that pass operands or do register spill fills, it's using locals to do that. There's the scratch pad. This you do explicitly program as the programmer. And that's when you do __ shared. That's what it's allocating. It's going to use that memory space. There's constant memory. This is just for constants. It's pretty boring. There's texture memory, which is for graphic stuff, which is not boring and actually kind of complicated. And we'll talk a little bit about how that works and how you can program that from CUDA if you need to. Texture memory used to be the only way you could get caching in CUDA. They didn't have the L1 caches. So if you were like a ninja programmer in early CUDA and you wanted your data to be cached, you'd have to use texture memory and access all of your vectors like textures to try to get it to actually be put in the cache. The upside of texture memory is that it's read-only. So you can't write to textures, at least and not use the texture cache. And we'll talk a little bit about how that works and how a texture cache is different from like a traditional cache. This local stuff is going to be cached in the L1D. There is a level 1 data cache here, the dedicated on-chip memory. We're going to have this sort of local scratch pad here for the shared memory stuff. There's a dedicated constant cache. It's pretty boring. It's just, it's just a small constant cache. There's a dedicated texture cache in the core. And then the global memory, which is everything that you ran CUDA malloc for, is stored in the HBM, and there is a cache hierarchy there. It's going to be cached in an L1 optionally. Like I said, it was normally not cached in the beginning of GPUs in CUDA. There was just no caching on any global accesses. And then there was caching to read-only data. And then there was no caching again. And then they brought back caching. And now there's caching on read-write data. So every generation, how they handle the global memory has sort of evolved and changed. In contemporary machines, they do cache in the local L1 this global data, but there's no coherence between cores. And so it's right back cached. You can modify values in the cache, but nobody else is going to see it unless your kernel ends. Okay, so while the kernel is running, they don't guarantee that there's visibility. But it is cached so that it's hopefully filtering some traffic. And we'll talk about how all that works in this slide set. All of this is cached in the last level cache, and GPUs, this is the L2. Okay. The terminology varies. In modern Hopper machines, they have an L0, an L1, an L1.5. Like they just didn't want to. You can call the levels whatever numbers you like, right? There's different levels of hierarchy. The last level cache in the GPU is generally called the L2. This is the thing that lives in the memory partitions that sort of stride it across the chip. And everything goes through here. Even when you do mem copies, it mem copies into the L2 first. Since it's a memory side cache, there's only one copy of anything. So you'll find that in really simple programs where your data is only a couple megabytes and it's L2 resident, if you profiled that, there's no access to global memory. And you'd look at that and go like, well, what the hell is happening? Well, when you did the mem copy, it actually mem copied it into the L2 and not into the HBM. So that way you just keep hitting on it. So if you have really small programs, they can live locally in the L2 and never have to use the GPU's HBM because the memcopy engine goes directly into the L2 cache. So what does this look like from a system perspective? So we've got each of these SMPTE cores, we connect them together into these clusters that have a single port access to the interconnect. What we're showing here is sort of a memory view of how the core looks. I showed you before the pipeline view of what happens with each stage. This is the sort of memory conceptually that there is on each core. The shared memory is its own, by definition, it's inside each of the SMPTE cores or inside each of the SMs, and every thread block that gets scheduled gets some piece of the shared memory. Okay, similar to the programming model that you're used to in CUDA, the shared memory gets divided up among the concurrent thread blocks that you can put on this core. The same thing happens with the register file. Both of these things happen when you spawn the kernel and you issue the thread block to the core. It grabs a chunk of each of these two spaces, and then it uses it for the duration of the thread block's life. For registers, it may not be the whole thread block. They may actually free some of the register space when the warps finish, but then for the shared memory, they have to wait for the whole thread block to finish because that's the definition of the programming model. It's alive at the whole time the thread block is alive. Also on chip, so what I'm showing here is like this is on chip storage, this is on chip storage, this, these are all on chip storage. There's SRAM in each SM to house all of these things. The constant cache, simple, boring, it's usually like a 4K read-only cache, stores stuff that you read from all the warps consistently, that's just a constant value. Texture cache, really funky graphic-centric thing, and then the data cache is where all the local and global data will end up being stored. From an SRAM perspective and a design efficiency perspective, the data cache is usually shared. The SRAM cells for the data cache is either shared with the texture cache. So this used to be true. Again, they keep changing design. In the early days, it was on its own, and then it was merged with the texture cache, and then they put it on its own, and they merged it with the shared memory. So today, from programming CUDA, that amount of L1 data cache you have is shared with the SRAM from the shared memory. So if you use more shared memory, you have less L1 data cache. It's kind of a nice natural way to split the on-chip SRAM. So they will conceptually share the same values or share the same on-chip storage. And we'll talk about how we actually construct such a unit that could do both in this slide set. After you get out of the core, you go to your interconnect, which is typically a crossbar, as we've mentioned, and then you'll traverse the interconnect, you'll go to the memory partition. Inside the memory partition is the off-chip DRAM channel. So this is the memory controller that orchestrates the HBM, gets the values from the HBM, buffers things, does the scheduling of memory accesses, etc. That fills into a last level cache bank. So this is one bank of that last level L2 that all accesses will go through, even the memory copies. And then there's reason to believe that the atomic operation unit, so if you want to do atomic global operations in GPUs, those don't get done at the L1s like they would in the CPU because there's no coherence. So all of the global atomics that need to happen on global memory have to go all the way out to the memory partition where there's just one copy of this value, and you can serialize the read, modify, write operations to the individual words. Okay. Questions on this? So this is a 10,000 foot view of the memory system. And then of course, this whole thing is like, not spawn, but like bolted together with a host, and they interface over PCIe or NVLink or something. Yep.
When we use cooperative blocks,
Yep.
every operation is being done on the memory.
When you use cooperative blocks, every operation is done in the memory part. What do you mean by that?
Because cycle here and
Within a cooperative group? Okay, so you're talking about cooperative group programming. Most people don't know about cooperative group programming. They haven't brought it up yet, but okay. Have I talked about this before? I mentioned it once, I think. So in the traditional programming model, that's what I've taught you so far. We've got shared memory and blocks, and then these things communicate. That's restrictive, right? So they've added hierarchies. They have a hierarchy called cooperative. It's cooperative groups, not blocks, right? There's a cooperative blocks, whatever. So basically, let's say that I made my blocks, and I did this based on my tiling, which is usually what you do. But then I want multiple blocks to be able to communicate, maybe not the whole kernel to be able to communicate, but maybe like 5, 6 blocks. I want them to be able to communicate. If I want that, then they may actually be on different cores, right? And so there's no guarantee that you're going to be able to do that local communication through something like the shared memory, like we do with the thread block, which would mean that if you want to guarantee coherence between all of these blocks that are potentially on different cores, then you're not caching anything. And every memory access has to go up through the L2, which by necessity makes that slower than otherwise. That's what you're saying, right? I don't know, do they actually advertise that that's the way it works, or are you just assuming that's the way it works? Yeah. I think it would depend, it would be really expensive to do it this way, to just assume nothing is cached, right? You just turn off all the local, all the on-chip caches. There's probably better ways to do this. I don't know, I've never actually programmed in cooperative groups, so I don't know if you're sort of marking the data that might possibly be shared, or you're not. If you're not marking the data, then it has to assume that anything can be shared, and then yes, unless they're actually going to implement some kind of coherence among subgroups of SMs or guarantee the scheduling of them on the same core, which I don't know, maybe that's what they do, then you have to go to the global memory, or at least to the memory partition. Okay. Good observation. Other questions? Okay. All right. Often these are implemented the same SRAM. Note L2 is banked across all memory partitions, blah, blah, blah. Okay, so let's talk about, again, we lifted this from a patent from the early noughts when they started fusing together the shared memory and the L1 cache. And, this is a pretty reasonable assertion of how you build an L1 cache that is merged together with the shared memory unit. Okay. So the interface to this is the output of our load store unit. So we're going to fetch, decode, issue something. And when we issue it into the load store unit. It's got some pipeline registers. And then once we've sort of triaged what memory unit it needs to go to, it'll then go to, this unit if it's the shared memory access or if it's a global or local memory access. Okay, it's going to triage all of that into this shared L1D/shared memory structure. Okay, so all of your instructions, which are just loads and stores, either to shared memory, to global, or to local, are going to come in here as step one. The SRAM array, so this is the actual, the big thing that's on the chip, right? The rest of the stuff is small. It's the control circuitry. The storage is what dominates the space, which is this big SRAM array. This is going to be shared and statically partitioned across the shared memory or to the L1D. And this can be reconfigured. So you can basically say, I'm launching one kernel and half of this SRAM I'm going to use as shared memory in this kernel. And then that kernel finishes, then another kernel comes along and it wants all of it for shared memory. And you can go reconfigure it to say, I want all of this for shared memory, and that will happen. Okay. Which means that I'm going to need to handle both accesses to shared memory and to the L1 data cache in the same program, technically. And I'm going to do it through this shared structure. Okay. This thing will support non-stalling interfaces, and we can do this with something called replay. So we don't necessarily want to stall if we have a bank conflict, for example. So in the shared memory, I told you that if you have a 32-way bank conflict, it'll take you 32 cycles to clear the shared memory. Maybe you don't want this one thing to hog the entire shared memory and sit in the pipeline register for 32 cycles as it clears. So there's a replay mechanism. Again, this is a design decision, but this is one way that they have built it in the past, where if there is a conflict, instead of just forcing that conflict to stall everything behind it, they'll replay the conflict from a place earlier in the pipeline, potentially somewhere in the load store unit or all the way back at the iBuffer. Okay, and just simply reissue the thing, depending on the design decision that they've made. So we can use, we can build this with a fully non-stalling interface if we make use of replay, and we can do this for L1 misses too. This is a very useful thing to do because, if you think about your 437 core, did you guys do MSHRs in 437? No, you didn't. There were no, if you missed, that was it, right? Everyone, the world is going to be behind me while I wait for this miss to fill. In GPUs, this is like god-awful disaster, right? Because that's my game, I need a bazillion misses at the same time. And I really only have 80 or 100 SMs, and if each of them can only miss once, like, you're not soaking up memory bandwidth. So they all need to miss a lot. So I need to miss and then miss under the miss and then continue to miss under the miss until I can miss no more, right? To soak up all of the memory bandwidth that I have available. And you can do that basically through a simple replay mechanism. And then you wait for the thing to come back, and then you replay the instruction once you know it's going to be a cache hit. That's essentially how this will work. And we'll sort of step through that in this slide set here. Okay. So let's go through some of these cases in a more detailed way. So there's 4 cases that we'll look at here. One is a direct map shared memory access. So this is sort of the simplest thing. You can sort of think of a shared memory access as like a direct map cache access where there's, you're going to one particular place, but you just don't have to check any tags, right? I know the data's at this index because you should have stored it there, and I'm just going to give you back the data that's in that location. Okay, so that's the simplest way to use this. Then we'll also take a look at coalesced and uncoalesced cache hits, and then cache misses. So what happens in this thing when that cache miss occurs? Okay. So let's say that we're doing a shared memory load. This is the sort of simplest conceptual thing that we can come up with. So the warp instruction, so again, this is one instruction for 32 different threads, is going to come down out of the load store unit and into this thing. And then the arbiter is going to try to figure out what's happening here. Are there bank conflicts with this shared memory load? You can tell this just from the addresses across all 32 of the threads, which are going to be in the pipeline register that you pass down. And then it's going to schedule those. It's going to say that, I have 7 conflict free that I can send this cycle. That leaves me, 15 that I need to send in another cycle or whatever. Okay. The arbiter is sort of taking those addresses and determining what bank conflicts exist, and subdivide them into those that can proceed and those that can't. And again, the schedule is heuristic, right? But the most sane thing to do is do the highest bandwidth first, like do the most accesses that you can right now, and then sort of delay the least accesses till later. It doesn't really matter because the instruction is still going to take that many cycles anyway. We don't actually, so let's say there's no conflicts. Let's say the programmer was kind and they made sure that everything was, strided by a float. So I know that I can access all 32 of these banks at the same time. It'll go through the tag unit. There's really nothing to do tag wise in the tag unit because we'll assume that it's in there because I'm not going to use any of that tag stuff for the shared memory accesses. If there was if there was a conflict, then I'm going to allow the non-conflicting ones to keep going, like I just showed, and then I'm going to kick back the rest of them to be replayed. So that way I don't have to stall a unit. So I can sort of keep trucking along with other instructions that want to come in here and use this unit. And how far back do you replay it? That really depends on the design. You already have one buffer in the system, which is the I buffer. Okay. So you can save area by just replaying from the issue stage, but you have to reissue the whole way through. Okay. And you also can't use that I buffer space with a new instruction. You're like blocking the front end of the pipeline, but you save area. If you don't put it in the I buffer, then you've got to have some kind of buffering somewhere else in the system, maybe a queue inside the load store unit, somewhere else. And that really is a design decision that the microarchitect makes on, is it worth it for me to add extra area to replay from a closer location, or should I just reuse the area from that I already have for buffering and then, essentially have more structural hazards in my front end. And what is optimal will really depend on how the program behaves. Right. And if I didn't replay, then my other option is stalling, which means everything behind me just waits, which is bad because there might be other stuff in flight that could still use these resources. Questions on this? Makes sense? Have you heard of replay before this? I think we do replay in 565, maybe a little bit at least, cache replay. So we're going to do that even for conflicts here on the shared memory. Because fundamentally, you're going to need multiple cycles to do this. Questions? Yes.
So if the first time there's going to be a conflict, so how replay going to help with it? Even like the second time we try there, like the conflict still there, or like the.
So yes. So let's say that I have a two-way conflict. That means I'll need 2 cycles. Okay. So let's say like it's accessing even banks or something across all the lanes. In the first cycle, you're still going to do that read of 16 banks. And then you're not you know, then basically you're gonna go later when you decide to replay the thing and get the other 16 banks, right? So it's not like you do nothing when you replay it. You do the little bit that you can. So it's like chipping away at the block, right, of all these accesses that you have. Does that make sense? Okay. If you wanted to guarantee latency through this thing, then you'd need to replay very close or just stall, right? Because then if you want to tell the programmer this is going to take 31 cycles to clear, then you can't do the replay because then it's variable because it'll depend on your schedule whenever you get replayed. So again, it really just depends on what you're guaranteeing the programmer for the latency there, but it will still do something, even if there's a conflict. It'll just do whatever it can this cycle. Does that make sense? Other questions? Yeah.
When you like do a replay, do you have to like tell which other like registers to look for next time it comes in? What do you mean? There's like a replay, you've already like given back 16 like memory accesses. You have to like give like a like, oh, next time you have to access only.
Yeah, so you can play with the active mask to fix that because remember, everything is implicitly across 32 lanes. And so this will come with an active mask that says these lanes are actually active. Only look at these addresses when I'm trying to resolve the conflict. And as you resolve more conflicts, you will essentially update what is effectively that active mask to say that I've, you know, by the end, there's only one lane maybe that's left to do the work. So you can use the active mask to do this. That's a great question. Does that make sense?
Yeah.
Yeah. Other question? Yep.
So if there is a conflict, could you fill in the remaining banks with a different port, or is that not?
I mean, look, if you change this unit, you could. If you allowed for sort of a dual read or an nth read. But now you're adding complication because now you've got more than one potential instruction flowing through. And so you could do something like what they do with the operand collector, right? Where you buffer a bunch of stuff and then try to fill in the holes. In general, it's less worth it here than it is at the operand collector stage. Because memory is slow anyway, right? Like memory's multi-cycle even if you hit in the cache. GPU cache pipelines actually tend to be pretty deep. Like it's not just the cycle if you hit in the L1, it's probably 16. If they're using a texture cache, it's like 80 cycles, which is ridiculous if you think about CPU world, but it's fine in GPUs because you can cover 80 cycles of latency and nothing matters. Makes sense. Other questions? Okay. All right. So yeah, we'll come back to replay when we talk about the non-conflicted address. We'll go through the non-conflicted addresses first. So for shared memory, we don't do any tag lookup. So we're assuming, let's assume now that we have a set of unconflicted and they're going to keep going through the pipeline. Oh, I'm out of time. I'm out of time. I'll let you go. Somebody logged off of Zoom and that reminded me that maybe I should check. You know, say, I'm done with this. Fair enough. Okay, I'm done. I'll come back and we'll finish this on. Oh, wow. After the break, you guys are not going to remember any of this. All right, I'll do my best to sort of speed us back to where we're here and then we'll finish this off after break. Okay, have a great break. Good luck with 666 exams for those of you brave enough to show up, and we'll see you in a couple weeks.
So, is this, yeah, like, what's the bandwidth of like replay?